Okay, in this video we are going to talk about the equation sum of torques acting about an axis equals the product of moment of inertia and angular acceleration. Let's go through the equation. We'll go through each element. I in the equation is moment of inertia. I've done a video on this. Make sure you understand moment of inertia. It's an object's resistance to change angular motion. And we know it's a function of how the mass is distributed about the axis of rotation. So we use this equation, sum of mass particles acting of the object, and how far those masses are from the axis of rotation squared is how we calculate moment of inertia. The units for moment of inertia, kilogram, meters squared. So kilogram meters squared. Versus inertia, which is just measured by an object's mass, which is just kilograms. And inertia by itself is an object's resistance to change motion. Moment of inertia is specific to angular motion. All right, alpha, we know from our kinematic section, is angular acceleration. It's rate of change of angular velocity, how fast angular velocity is changing. And we use the equation alpha equals delta omega over delta t, and the units are radians per second squared. If you remember, when we did angular kinematics, we actually had some options for units. That would be degrees per second squared, revolutions per second squared, any units of angular velocity over any units of time. However, when we're using angular acceleration outside of just looking at position velocity acceleration relationships, we have to use radians per second squared. Radians are unitless parameter. It's the measure of an arc relative to the radius of rotation, and so it's units of distance over units of distance. The important aspect is once we start doing a unit analysis is these are unitless, so we take them out of our unit analysis. So let's do that right now, actually. Let's look at a unit analysis because we have two things on opposite sides of the equality. Oh, I've got one more thing to do before I do that. Torque, we're going to use this equation, which there's a separate video on this equation. It's magnitude of force times an object's moment arm, and you want to be able to identify the moment arm of an object graphically. The units are units of force times units of distance, so Newton meters. Now we get to the equation, we'll go back to this, sum of torque equals I alpha. Here's where I want to do the unit analysis because we've got an equality sign here. We've got torque on this side of the equation and the product of moment of inertia and angular acceleration on this side of the equality sign. The units have to be the same on both sides. It's just good to make sure we have our units down for each of these parameters. So let's do a unit analysis. We'll look at the units of each of these and make sure that they're equivalent to each other. So I'm just putting the units in for each parameter. I've got torque units, Newton meters, equals moment of inertia units, kilogram meters squared, and angular acceleration units, radians per second squared. These have to be equivalent units to this because of the equality sign. All right, let me just write that out a little bit more. Well, actually, I'm going to write it out again so I can show you that I'm going to take out radians from this unit analysis because radians are unitless. The radians are distance over distance. Okay, it's a radian is, I draw here a circle and I take the radius of the circle and I rotate it through some angle. This would be R and this would be S, and this would be the angle. A radian is a ratio of how long this arc is to how long the radius is. So it's units of length, meters, over units of length, meters, so they're unitless. So I'm crossing them out, and I'm left with kilogram meters squared per second squared. It still doesn't look like Newton meters, so I'm going to rewrite this part right here a little differently. I'm going to write kilogram meters times meters. So that's my meters squared divided by seconds squared, which is still the same denominator. Remember, a Newton is mass times acceleration, so kilogram meters per second squared. Now let's, I didn't do that, but here you can hopefully see that right there is a Newton. So now we're left with newtons times meters, which is the same set of units as torque. All right, so that's our unit analysis, and we need to make sure that we understand units for torque, units of moment of inertia, and units of angular acceleration, and how they work together to ultimately yield Newton meters. Okay, one more thing we want to do in this video is go through the steps to do an angular kinetic analysis. So now that we have this equation, sum of torque equals I alpha, how do we use that? And when do we use T equals FD perpendicular? I'll just break this down into a step-by-step process. When we do an angular kinetic analysis, the first step is we want to identify the torques acting about the axis. In order to identify the torques acting about an axis, first thing we do is identify all forces acting on the object, okay, about the axis of rotation. Remember, if a force acts at the axis of rotation, the force will not tend to rotate the object, and it will not create a torque. So we want to identify the forces acting on the object, and mostly forces that are acting away from the axis of rotation. Once we have identified the forces acting on the object, we're going to use this equation, T equals FD perpendicular, for each force that we have acting on the object tending to cause rotation. If we have 3 forces, we'll have 3 torques. If we have 2 forces, we'll have 2 torques, so forth. Okay? Once we identify the torques, then we're going to make sure that we assign a direction to each torque, and we'll use counterclockwise is positive as our reference frame for just about every problem that we do. There's times that we'll switch it, but we don't need to, and we can work with the one reference frame. Remember, that reference frame is just as logical as saying up is positive. Excuse me. Okay, so then once we have that information, we are going to put all the torques with the directions assigned to each torque on this side of the equality sign, and then on this side of the equality sign, we'll need to know moment of inertia and angular acceleration. So in another video, I'll go through some practice problems on how to use this equation and how to do an angular kinetic analysis. Okay, thanks everybody.